The Corner Point Theorem. Welcome, everyone. Before we dive into today's new topic, let's take a moment to recap what we have covered so far. In our previous lessons, we learned how to identify and define a feasible region. As you remember, this is simply the specific area on a graph that satisfies every single constraint we are given in a linear programming problem. Now, here is the problem we face. Once we shade that feasible region, it actually contains an infinite number of individual points. If we wanted to find the absolute maximum or minimum value for our objective function, which we represent as z equals a times x plus b times y, it would be physically impossible to test every single point within that area. We simply don't have the time or the resources to calculate an infinite number of values. Fortunately, we don't have to. This brings us to the core of today's lesson, the Corner Point Theorem. Think of this as a mathematical shortcut. This theorem tells us that we can skip all those infinite points in the middle and focus our attention only on a few specific, critical points, the vertices or the corners of our feasible region. By checking just these few points, we can find our optimal solution with total confidence. In the next slide, we will look closer at exactly what defines one of these corner points. Understanding the corner point. Now, before we dive into the actual theorems, we need to be very precise about what we mean when we say corner point. By definition, a corner point, which you might also hear referred to as a vertex, is a specific point within our feasible region that is formed exactly where two boundary lines intersect. To put this into practical terms, imagine you have two constraints represented by the linear equations, x plus y equals 10 and 2x plus y equals 15. The exact spot where these two lines cross each other on your graph is what we identify as a corner point. It is helpful to think of these points as the extreme limits of your constraints. They represent the very edges of your possibilities, marking the boundaries where your constraints meet. Understanding these specific points is crucial because, as we will see in the next slide, these are the only points we truly need to focus on to find our optimal solution. The fundamental theorems. Now that we understand what a corner point actually is, let's look at the mathematical heart of this topic. On this slide, we are exploring the two primary theorems that provide the theoretical basis for solving linear programming problems graphically. First, let's discuss Theorem 1, which focuses on the location of the optimal value. This theorem states that if an optimal value, meaning either a maximum or a minimum, of our objective function, z equals a times x plus b times y, actually exists, then it must occur at one of the corner points of our feasible region. To put this in simpler terms, you don't need to waste time testing every single point inside that shaded area we found in the previous lesson. If a best answer exists, the theorem guarantees that you will find it at one of the vertices. Next, we have Theorem 2, which deals specifically with bounded feasible regions. Now, remember from our earlier discussion that a region is bounded if it forms a closed polygon and doesn't extend off toward infinity. This theorem tells us that if the region is bounded, the objective function z will have both a maximum and a minimum value, and both of these will occur at the corner points of the region. Essentially, if you are working within a closed shape, you are guaranteed to find both your highest and lowest possible values just by testing the vertices. This brings us perfectly to our next slide, where we will see these two theorems put into practice with a real-world bakery example. Real-world application example. Now that we have understood the theory behind the corner point theorem, let's put it into practice with a real-world scenario. Imagine you are running a small bakery. You produce two types of cakes, chocolate cake, which we will represent by the variable x, and vanilla cake, represented by the variable y. Your main goal, or your objective function, is to maximize your total profit. For every chocolate cake sold, you make 500, and for every vanilla cake, you make 400. So, our profit equation z is equal to 500x plus 400y. Now, as we discussed in the previous slides, you can't just bake infinite cakes because you are limited by oven space and ingredients. After plotting all these constraints on a graph, you've identified your feasible region. In this specific case, the region is a bounded polygon, meaning it's a closed shape. As we learned from Theorem 2, this means both a maximum and a minimum profit definitely exist at the vertices. We have identified 4 corner points for this bakery. Point P at 0, 0, point Q at 0, 10, point R at 6, 7, and point S at 12, 0. Let's walk through the 3-step process to find that maximum profit. Step 1 is simply identifying our corner points, which we have already done. They are 0, 0, 0, 10, 6, 7, and 12, 0. Step 2 is the most important part. We need to evaluate our profit function, z, at each of these specific vertices. First at point P, which is 0, 0, 500 times 0 plus 400 times 0 gives us a profit of 0. Next at point Q, which is 0, 10, 500 times 0 plus 400 times 10 gives us a profit of 4,000. Then let's check point R, which is 6, 7, 500 times 6 is 3,000, and 400 times 7 is 2,800. Adding those together, we get a profit of 5,800. Finally, let's look at point S, which is 12, 0. 500 times 12 plus 400 times 0 gives us a profit of 6,000. Step 3 is to compare these results. Looking at our values, 0 is less than 4,000, which is less than 5,800, which is less than 6,000. In conclusion, by applying the Corner Point Theorem, we can clearly see that the maximum profit is 6,000. This occurs at corner point S, which is 12, 0. This tells the bakery that to achieve the highest possible profit, they should produce 12 chocolate cakes and 0 vanilla cakes. As we will see in the next slide, it is important to remember that we didn't need to check any other points inside the region, because the theorem guarantees the answer is at one of these vertices. Common mistakes to avoid. First, let's talk about checking interior points. I have seen many students pick a point right in the middle of the shaded feasible region, thinking that a value somewhere in the center might yield a higher result. However, remember what we discussed in the previous slides regarding the corner point theorem. The math guarantees that the optimal value is pushed to the extreme limits. Therefore, testing points inside the region is a waste of your time. You only need to focus on the vertices. Second, do not ignore your non-negative constraints. In almost every linear programming problem, you will see constraints stating that x is greater than or equal to 0, and y is greater than or equal to 0. It is easy to get so caught up in the complex intersection points that you forget the axes themselves are boundaries. This means the origin, or the point 0, 0, and the points where your lines cross the x and y axes are often your most critical vertices. Finally, a word of caution regarding unbounded regions. In our previous slide, we noted that for a bounded or closed polygon, both a maximum and a minimum are guaranteed. But be very careful if your feasible region is unbounded, meaning it opens up and extends toward infinity. In such cases, while you might find a minimum, a maximum might not exist at all because the value of your objective function could simply keep increasing forever. Now that we have seen how the theorem works in practice with our bakery example, I want to pause and discuss some common pitfalls. Even when you understand the logic, it is very easy to fall into certain traps during an exam. Keep these traps in mind as we wrap up with our final summary of the key takeaways. Key takeaways. First, let's revisit the definition of a corner point. Remember, a corner point, or what we also call a vertex, is simply the specific point where two boundary lines of your feasible region intersect. It is that precise meeting point of your constraints. Next, think about the concept of efficiency. As we discussed in our first slide, a feasible region contains an infinite number of points, which would make testing every single one impossible. The beauty of the corner point theorem is that it simplifies linear programming problems by reducing that infinite sea of points down to just a few finite, manageable vertices. Third, keep the rule for bounded regions in mind. If your feasible region is bounded, meaning it forms a closed polygon and doesn't extend forever, you are mathematically guaranteed to find both a maximum and a minimum value, and both will be located at the corners. Finally, let's summarize how to identify the optimal solution. Once you have evaluated your objective function, which we've written as z equals a times x plus b times y, the process is straightforward. The corner point that yields the highest value of z is your maximum, and the one that yields the lowest value is your minimum. All right, we have reached the end of our lesson. Before you head off to practice these problems, let's quickly recap the key takeaways from today's session to ensure everything is clear. If you can master these 4 points, you have mastered the core of the corner point theorem. Great job today.